Hello everyone, I am Zach Peterson. Welcome back to my channel, and I'm here to answer all of your questions about PCB design. Today we're going to be looking at partial HDI stackups. Just recently in iConnect 007, there was an article that was published about this type of stackup, and just recently I received a viewer question about this type of design. That's what we're going to look at today, and we're also going to look at some design examples inside of Altium Designer. Let's go ahead and get started. So before we get started looking at some design examples, let's take a look at that viewer question. Thomas Lovskog writes, "Hi Zach, my name is Thomas and I am a PCB designer / electronics engineer. I attended your seminar 2 years ago in Copenhagen and got your name a while back, I must admit, from Michael Schack at Azatec. Last year in the October edition of Design 007 magazine, I read about partial HDI. Is this anything you have encountered or have any thoughts about?" So the answer is yes, this is something I have encountered and I have used in several designs. And I never knew that it was actually called partial HDI. I always called it like hybrid HDI because it was usually done on hybrid stackups, but they're really the same type of design. So let's take a look at this article description on the iConnect website. Here you can see that they describe partial HDI as the targeted use of HDI, usually on one section of one layer of a PCB. It offers designers an avenue for escape routing from BGAs with a pitch of 0.5 millimeters or less when a mechanically drilled plated through hole is impossible. So you have HDI relegated to one layer of the board, and that reduces the number of sequential lamination cycles that you need to fabricate this PCB. Now what they're describing is the use of HDI with laser drilled microvias in order to fan out fine pitch BGAs, and they mentioned 0.5 millimeters or less. And I have done that on some designs. However, I've also done partial HDI designs where the HDI layers are using mechanically drilled vias. So they're using 6 mil or 8 mil mechanically drilled blind and buried vias. So the takeaway is you don't have to use it with laser drilling. The folks at iConnect have just described it using laser drilled vias. Now you could use it with larger BGAs all the way up to 1 millimeter pitch, or you could use it in designs that don't even have a BGA, and there are use cases for that as well. So what I want to do now is take a look at two design examples that really illustrate the different use cases of both types of partial HDI stackups. One that uses mechanically drilled blind and buried vias, and then another that uses laser drilled microvias. So the first design that I want to look at uses mechanically drilled blind vias to form a partial HDI stackup. And this design also happens to be a hybrid HDI stackup because it mixes PTFE laminates with standard FR4 grade laminates. So here on screen, we have the 4-chip Cascade radar design from Texas Instruments. And I have shown this example in some of my seminars as well as in other videos, for example, on the Altium Academy channel. And we've actually taken this design and scaled it up to 6 chips and higher numbers of chips for some very unique radar systems. So before we look at the stackup, let's take a look at the PCB layout. If we zoom in here, we can see what's going on the top layer, which is where the partial HDI layers are located. So here you can see that we have a bunch of chips on the top layer, and these chips are BGAs, and those are the radar transceivers. And you can see here we're routing out from these radar transceivers in these coplanar waveguides. And then these coplanar waveguides all route into the antennas that you can see here near the top side of the board. Now, if we just zoom in here into the footprint for this BGA and we just measure the pitch, we can see that the pitch is 0.65 millimeters. So it's not the finest pitch BGA, but it is small enough that you would need 6 mil vias in order to route into the inner layers. Now, Texas Instruments didn't really use the partial HDI design approach in order to do escape routing out of this chip. And in fact, if you just look around the ball out here around the edges, you'll see very few vias being used to route into the inner layers. What you will see though is that most of these vias along the edge of the chip and then leading along the edge of these coplanar waveguides are all blind vias. And so that's where the partial HDI approach comes from. So let's take a look at the Stackup. Here, if we look at the Stackup and we go over to the via types tab, you can see here where these blind vias are being used. They're just being used on the outer layer, and you can see here they're being used to span from layer 1 to layer 2. Now, these vias could have been done as micro vias. That's perfectly reasonable in this type of design, but it's not really required because they're not being used to fan out from a fine pitch BGA. As I mentioned before, these vias are being used to line coplanar waveguides on the top layer of the board. Now, coplanar waveguides that connect to the internal ground lane with coplanar ground on the top layer need to have stitching vias somewhere, and you get the highest signal isolation along this interconnect if you place them right along the edge of the coplanar ground on the top layer. Now you might ask, why didn't we use through holes here? Well, let's take a look at an internal layer. If you look at some of these internal layers, you actually see a lot of signal routing on these internal layers. And you can see that this signal routing is passing right underneath the path of these coplanar waveguides. So it should be pretty obvious. If all of these blind vias on the top layer were instead through-hole vias, you wouldn't have any room at all to route any of these signals anywhere on the board. So in this type of design, we actually need to take the partial HDI approach with only the outer layer having mechanically drilled blind vias, but not for the reasons of fanning out a fine pitch BGA. Let's take a look at another design in Altium Designer. Now, this design is for the NRF52 module, and you can download the project files for this example design from my website. I'll also link to the project video that we did on the Altium Academy channel in the video description. Now in this design, if we go into 2D, we can see here that we also have a BGA, and if we just measure the distance between the pad centers, you can see that we have a 0.35 millimeter pitch BGA. So this more closely aligns with the type of design that was mentioned in the iConnect article. Now, if you look around the footprint for this BGA, you can see that we have a lot of ground pads in the center, but you can also see that we're using 1 to 2 and 1 to 3 layer transitions with vias in order to fan out all of the pins on this BGA. So let's take a look at the PCB Stackup. Here inside of the Stackup, you can see I have the via types tab active, and you can see here that we have the standard through-hole via as well as blind and buried vias, but only on the top half of the Stackup. So again, this more closely aligns with what we saw described in the iConnect article. So here the blind via just goes from layer 1 to 2, and then the buried via goes from layer 2 to 3. Now, if you zoom in here and you select one of these vias, you can see here that the hole size is only 4 mils. So this would essentially be a laser drilled microvia type of application. And of course, inside of Altium Designer, you have an option to select microvia inside the layer stack manager. So I probably need to update the design files with that microvia definition. But in any case, when you send this off to a fabrication house, they will review all of your drill data. They'll see that these are 4 mil holes. And of course, they'll tell you, hey, these need to be laser drilled. Now, you could go even smaller with the hole diameter if you needed to design to a higher reliability application, but that's going to get tough because, again, take a look at this layer Stackup. Right now, if you calculate the aspect ratio for these vias on the top layer and on the transition from layer 2 to 3, you'll see here that a 4 mil hole diameter and then a 4 mil dielectric thickness gives you an aspect ratio of 1 to 1. Now that's really pushing the limits of what you can do with stacked microvias. Now it's not that you can't fabricate them, it's just that there's a reliability risk if you have these 1-to-1 aspect ratio vias. Now we've fabricated a design that is very similar to this that uses these types of microvia stacks, and of course we don't know what the yield was because we sent this into a quick turn prototyper, but we did get boards back that were assembled and that functioned correctly. So it is possible to manufacture this. However, if you were going to take this design and use it at scale, what you should instead do is make this dielectric thinner and try to get your via aspect ratio below 1 to 1. So if we wanted to go to a higher reliability application for these vias, we would instead want to switch these vias to, for example, a 3 mil diameter hole, or maybe even a 2 mil diameter hole, as long as the fabrication house can produce that on this material. Then we would want to take our dielectric thickness and we're going to make that a lot smaller. We may need to make that 3 mils or 2 mils or even 1.5 mil, depending on what materials are available. So this is a really challenging design to work with when you look at it from those aspects, especially when you want to get to a high reliability application. And getting high density designs to also be highly reliable is really a challenge, especially when you start looking in areas like medical or automotive or military and aerospace. So if you are going to reuse this design, make sure you consider those aspects, and in particular that microvia aspect ratio. But again, this is a really great application for a partial HDI board. I don't need to have the entire design filled with these blind via transitions from the bottom layer into the inner layers. I really only need those blind and buried via transitions on the outer layers, and it's just to fan out this one component on the top layer. So again, an ideal use of a partial HDI design. Now, if we had a variant of this design with, let's say, BGAs on the top side as well as the bottom side, then we would no longer have a partial HDI design. We might also need to have blind and buried vias going from the bottom layer into the inner layers, and then we're going to have pretty much a standard HDI design that uses one of the standard HDI stackups. So just to conclude, if you are going to do any kind of partial HDI stackup and you're going to use small diameter mechanically drilled or laser drilled vias, make sure you check with your fabrication house. Your fabrication house is going to be able to tell you the aspect ratio limits that you need to enforce for those vias that you want to use on the outer layers in this partial HDI design. And really that guideline applies regardless of the type of HDI stackup you use. Doesn't matter if it's a partial HDI or a standard HDI stackup. Once you get that aspect ratio limitation and then you figure out the via diameter that you can use in that BGA or on that HDI layer, you can then determine what layer thickness you need to have or what dielectric material thickness you need to have, and then you can shop around for the materials that are going to work best in your design. I'm going to do another video about these high density fan outs coming up soon, so make sure to hit the like button and subscribe to the channel to see that video and learn more. Thanks for watching this video, everybody. I always love getting your comments and questions, and if you ask a great question, it just might end up in one of these videos. Make sure to subscribe for more great PCB design content, and I'll see you next time. Thanks, everybody.